Okay, boys and girls, welcome to the new part of this course, and this is the actual we're going towards the end of the course. But this is a very, very important little topic, and it's called regression analysis. And I just want to introduce you to this because it is so important. You've almost certainly seen this before in some form or other, maybe when you're trying to interpret experimental data. And the basic idea is this. You've got two columns of numbers. In each of the columns, you have the same number of numbers, and you suspect that there's a relationship between the two columns. Okay, so this is the basic idea. All right, your engineering intuition tells you that there's a relationship between the two variables. As you increase one, the other increases, or as you increase one, the other decreases. And you would like, because you're an engineer, you would like to get a formula linking one variable with the other variable. Because if you did that, you would be a superstar. Okay, so you would be an engineering superstar if you could do that. Because the reason why that is important is because instead of then dealing with data, you can deal with a simple formula. And no matter how much data you have, you're condensing all that data into a very, very simple formula. And that formula summarizes what's going on between the two variables. And that's basically what we've been doing, what you did with Abdel. Summarizing is what data analytics is all about in a lot of the time. Okay, and so this is what we want to do here. You've got two columns of numbers. You want to summarize the relationship between those two columns of numbers in a single formula. All right. Now, the relationship we're always looking for in engineering is a linear relationship. So if you plot the data between the two, if you plot each couple of numbers in the two columns as a data point, all the data points lie pretty close to a straight line. And in that case, we said you have a linear relationship. And the reason why linear relationships are so important is because if you have a linear relationship, you know the formula between the two variables. Let me call the two variables A and B. Or let me call them Y and X. If there's a linear relationship between Y and X, then you know what the formula between Y and X is. Y is equal to A plus BX. Okay, because that's the equation of a straight line. If the relationship, when you plot the relationship, is not a straight line, you're screwed. You don't know what the relationship intrinsically is. The relationship between the two variables is said to be nonlinear, and in the nonlinear case, the problem is that you have an infinity of choices. You can choose anything. There's an infinity of choices for nonlinear, whereas if you have a linear relationship between the two variables, there's only one choice. And that's what makes linear relationships so important, especially in data analytics. Because if you have a linear relationship, you know exactly what the formula is. You know it's Y is equal to A plus BX. And all you have to do then is find out the number A and find the number B. A is called the intercept and B is called the slope. So what we want to do is we want to find out what the A and B are for the two columns of numbers that we're interested in. All right, and in OR, there's some inbuilt functions that should make this ridiculously easy. All right, now, ignore that, folks. So let's look at a set of data set. Now, as I said to you guys, there's a number of inbuilt data sets in OR. And these data sets have been chosen to illustrate different aspects of data analytics. And one of the data sets is called CARS. And I just typed it in there, and you see what it is there. You see there's two variables. There's speed and there's distance. Now, as engineers, you know what this is. I think what this data set is about. It gives the relationship between the stopping distance for a particular speed. So if you're going at a speed of 10, you could either stop at 18, 26, and 34. It depends on what type of car you have, or your reactions as a driver, etc. But that's basically the idea. Okay, and I think we all agree, I'm not an engineer, but as engineers, you would suspect that the faster you're going, the longer the distance you need to stop. Okay, so you would suspect that these two variables are said to be positively correlated. As you increase the speed, the distance also increases. So that's what we're looking for here. Okay, so that's what we're going to try and investigate to see if that's true, if our intuition is true, is good. All right, so that's it. Now, if nothing else, This is your, you'll be in college for 4 years. Okay, admittedly this year I'm not sure if this counts or not because it's such a terrible year. But if nothing else from your 4 years in engineering education, here's what I want you to take away from that. If you've got two columns of numbers, folks, and you suspect there's a relationship between the two columns of numbers, and even if you don't suspect there's a relationship between the two columns of numbers, plot the bloody data. Always do this. Two columns of numbers before you do anything else. You plot it. You just plot the numbers and see what happens. See what the plot is telling you. So in this case, fortunately in R, the plot function is called plot. And because I've only got two variables in this data set, I can just put in the name of the data set. I get this relationship here. Now, as students, because you're young and you're idealistic, yeah, you probably are you feel a little bit dirty and unclean by assuming that there's a linear relationship in this case. If you look at this data plot here, okay, it doesn't seem as if it's not a very close linear relationship, but you can imagine a straight line going through all that data. And if you can imagine a straight line going through all that data, then you have a linear relationship. I'll show you examples in a second now, folks, where it's pretty obvious that there isn't a linear relationship. But in this case, although it's not all the data points aren't very tight to a straight line, you can imagine a straight line going through this pretty close to all the data points. And you have to be nice to yourself, and you have to be nice to the data set in this case, especially in the real world. In the real world, nothing is perfectly linear. It's in the real world, it's probably not even as good as this. But this is an example of a situation where you have to be nice to yourself and to the people around you and to the data set and to the people you're working for, and assume that there's a linear relationship between speed and there's distance. So the question then arises is, well, what is that linear relationship? And there's a very, very powerful function in R called the LM function. LM stands for linear model, which gives you the A and B numbers in the relationship between distance and speed. Okay? So let me show you what that is. It's very easy. So always, guys, you do the plotting first. This is called visualization. Now, you'll hear this a lot in data analytics, and you'll hear a lot actually in just when you start working in for a company in the business world about visualization being so important these days, and it really is. Yeah, plotting things is the way to make money these days, and the plot function in R, and this is just base R now here, folks. So there's much more sophisticated plotting functions, but in base R, that plot function I think is really, really nice. Okay, and it gives you a very, very quick way of identifying if there's a linear relationship or not, or an approximate linear relationship, folks. That's all we want most of the time, an approximate linear relationship. All right, so we've got two columns of numbers. We plotted them, and we've convinced ourselves that yes, a linear relationship is appropriate here. What is that linear relationship? What are the A and B numbers? So let's do that. So let's look at LM of cars. Oh, sorry. So now, because I've got two linear relationships, or two columns here, I can do this. So LM cars, if I do that, here's the formula. So the intercept is the A number, and the slope here, the other number is the slope. And what's very, very important here, folks, is that this formula outputs the speed is equal to 8.2839 plus 0.1656 times the distance. Okay, so the independent variable in this case is distance, and the dependent variable is speed. So what we have here, guys, is speed equals 8.2839 plus 0.1. Oh, I can't do anything anymore. 1.656 star. So be very, very careful. You've got two variables. So you want the formula to reflect your output from the LM function. So in this case, what you have here, folks, when I just did pure LM curly brackets or open brackets cars, that's the relationship I got. Okay, you can see where the 8.2 and the intercept value comes from, but make sure that the speed is on the left-hand side and dist is on the right-hand side, multiplying the 0.1656. Now, suppose you say, well, I don't want that relationship. I want the relationship between the more natural one, I suppose, of dist being a function of speed. Now, again, folks, that's just nonsense here because that's not, I just wrote that down there just to illustrate what the formula is. Okay, so now suppose I want the dist to be the dependent variable. And in this case, you can use LM function again to force that. So what you do is you have cars, dist, tilde, cars, speed. Now, in this case, what you're doing is you're telling OR that you want the dependent variable to be dist and the speed variable to be the independent variable. Okay, so when I do that, folks, this is what I get. So in this case, now what you have is in this case, if you've got two variables, you have a choice. You can either go with the first one here. Oh, I'm sorry, folks, I can't find that arrow. So you can either do the first one for speed in terms of dist, or you can do the second one here, which is dist equals minus 17.579 plus 3.932 star speed. And you have a choice. You can go one or the other, it doesn't matter. Which one is better? It doesn't matter. It's I suppose it's a choice. In this case, I suspect though that speed is the one that you can imagine as the cause, and the effect of the speed then in terms of distance is the distance. So you'd have the distance on the left hand side and speed on the right hand side. But you can go back up here, guys, and if you want to, if speed turns you on, then you put speed on the left hand side and distance on the right. It doesn't matter. But usually there is a natural one to assume happens first. So in this case, we're driving along at a certain speed. We need to stop suddenly, and so therefore we do the dist after the speed, if that makes sense. All right, very good. So now let's have a look at that then. Let's see if that makes sense. So okay, again, folks, speed not found. That's okay because I'm just using these formulas here to illustrate, to give you what the formula is. Right. So let's look at how well the straight line fits the data, I suppose. So let me just do this again. Let me just do the cars dist thing here. Now let me just do it again, plot. Now in this case, if I'm going to have, just to be sure, I'm going to put my speed along the x-axis. So I'm going to have cars speed here. Now, of course, in OR, the first argument in the plot function is on the x-axis, and the second one is on the right axis, as on the y-axis, the vertical axis. So that's what I'm going to do. Hopefully that works. Yeah. And then what I'm going to do, folks, is I'm going to come back and I'm going to add. Sorry, I'm going to put abline. And I'm going to put in this. And then when I go back here, I get my regression line fitted to my plot. All right, so that's what you get. So that's the regression line going through the data points. Last year, in second year, if we remember, when we were actually toe to toe, cheek to cheek in lecture halls, I showed you where the regression coefficients come from and why the regression line is the way it is. But from now on, you don't even need to know that. You just use OR. And you see the regression line is pretty close to the data points as it should be. Now, guys, as I said, now the reason why this is so important is because now you're laughing because you've condensed two columns of numbers into a single formula. So if you know, so suppose you're driving along at speed 40, yeah, and you want to figure out, well, I'm driving at 40 now. If I had to stop, how long would it take me? Well, what you do is you put in your minus 15, minus 17. Sorry, guys, if I come back up here, I'm going to focus. Just going to copy this here. I'm going to copy that. I'm going to paste it. And I'm going to replace the speed. And suppose you've got 40. And you see, folks, at 40, the stopping distance is 139.7, which would be about 140. Now that doesn't make sense. Oh, it does make sense. Yeah. It does make sense. Yeah. So if I was driving at 40 and I wanted to figure out the distance, then I would replace the speed by 40 and I get this. Okay. If I was driving along at, we say, 20, what would I get? I would get that. Fair enough. If I was driving along at 10, what would I get? I'd get that. Okay. So that's very simple. You replace the speed variable by the value of the variable that you're interested in. 40, 20, and 10. Now here's something very, very important, folks. This is really important. Actually, this is very, very important part of regression. People misuse regression. Okay. Now, the reason why I start with 40 here and then I went 20 and 10 is that if you go back to the original data, folks, and you look at the speed, you see here that the speed of the data that you're given goes from 4 up to 25. Okay. Now, so the range of speed for which your regression formula is appropriate and can be used goes from between 4 and 25. Any number outside that range, you're going to be very dubious about how good the prediction is going to be. So if you go back here and you look at my speed for 40, I got 139.7. The reason why I was a little bit hesitant and a bit when I stumbled there is because I knew that was a bit big. But then I realized that 40 was outside the data range. So I was actually okay. Hey, it all works out in the end. Okay, 20 and 10 are good because 20 and 10 are within the range of the data. So you would expect the prediction, which is what these numbers are going to be good predictions. The prediction from 40, it's an answer and certainly better than nothing, but you can't be very sure about it. And that's very, very important. 40 is outside the range of data. You are not confident about using that. 20 and 10 are within the range of data and you would be confident about using those values. And as a check, folks, you see here as a speed of 10, we're getting a stopping distance of 22. If you go back up here, 10, we see, look, it's 18, 26, and 34. So we're right bang in the middle. So we're good. So this regression formula works. Okay. Now, let me go back to right. Let's go back to my plot on my regression line. Whoa, why doesn't that work? Sorry, guys. I'm sorry. Now, for some reason, it won't let me do that. Let me just do this again. Let me just go back up here because this worked before. I'm going to plot this. And then I'm going to go back to it. And then I'm going to get my ab line for my linear function. And then I'm going to look at this. So sorry, but the first time it didn't seem to work. R has its own peculiarities. Sometimes it works, sometimes it doesn't, depending on the day of the week and the way the wind's blowing. But in this case, look, folks, we will see here the regression line and the data points. Now, you can tell how good your linear plot is, or how good the fit is, as we say in statistics, how good the fit is to the data by calculating what's called the correlation coefficient. Okay, so the correlation coefficient is very, very important. It's between -1 always. The values are going to be between -1 and +1. Okay, that's very important. If, as you see here, guys, the regression line is sloping upwards, the correlation coefficient is going to be positive, and so therefore it's said to be positively correlated. If, on the other hand, the regression line was sloping downwards as you move from left to right, the data would be said to be negatively correlated. So to calculate the correlation coefficients in R, it's very, very easy. Now, in this case, folks, if all the data points were right on top of the regression line, the correlation coefficient would be very, very close to 1. And ideally, that's what you want. You want a correlation coefficient really, really close to 1. In the real world, folks, that's not the way it happens. So anything above 0.75, 0.8, maybe 0.9, again, this is very subjective, would be a good correlation coefficient. Now, in this case, you can tell reasonably well how good it's going to be. I think the correlation coefficient here is about 0.8. You know, it's okay, the data fit is reasonable, but the data points aren't very tight to the straight line, so it's about 0.8. I know it's going to be positive because the regression line is sloping upwards. And I know it's not going to be close to 1 because they're not all very close to the regression line, but certainly they're going to be somewhere close. They're going to be about 0.8. Okay, so the way you do that here is you do core, and in this case I type in cars because cars is I've only got 2 variables in cars, and then you see what the correlation coefficient is. The correlation coefficient between the speed and speed is 1. Okay, that's perfectly correlated because if you know the speed, you know the speed. But the correlation coefficient between the distance and the speed is 0.8068949, so it's 0.81. Which is what I did, which is what I suspected, and I hadn't done this before, folks. I'm just this good at interpreting scatter plots, and that's what we have here. We've got the plot of the data, and the regression line is called a scatter plot. So in this case, folks, the regression line and the correlation coefficient to the regression line is 0.81, which is pretty good, and so therefore I have a reasonably good fit of my straight line to my data. Okay, now I'm going to stop here. And this is the end of regression 1. And I'm going to continue on. I call it intriguingly regression 2. After I was going to take a break here and then come back and do regression 2. Okay, thank you very much, guys.